Okay, good morning, everyone. We uh, we will be doing planes in 3D. Our group members are Ms. Premati Puran, Ms. Jaya Siratan, and myself, Abby Prasad. Next slide, please. So just a little overview of the presentation. In the presentation, we will be defining key terms. There will be an introduction to planes in 3D. We will be defining a plane and showing you the vector representation of a plane. We'll be explaining the cross product and dot product of a plane, the normal vector, the Cartesian equation of a plane, and the intersection of planes. Next slide, please. Okay, so before we start the presentation, I'm just going to define some key terms so that everything makes more sense, hopefully. So a plane in 3D is a flat surface in three-dimensional space that extends infinitely in all directions. A 3D coordinate system is a system used to locate points in space using three axes, unlike the two axes that we're accustomed to for lines. A plane equation is a mathematical expression of a plane written as ax plus by plus cz equals dax plus by plus cz, which is equal to dax plus by plus cz equals d. And all these letters A, B, C, D, A, B, and so on are constants. A normal vector is one that is perpendicular or at 90 degrees to a plane. The word perpendicular basically means where two lines or vectors meet right at a 90-degree angle. So a vector is a quantity that has both sides and direction. A scalar quantity is one with magnitude only. It has no direction. So the components A, B, and C, these are the values of a vector along the x, y, and z directions. The orientation is the direction or positioning of a plane in 3D space. The Cartesian coordinates is just a system used to define points using ordered triples. The point on a plane is any location that lies exactly on the flat surface of a plane. The direction is the way something is facing or pointing in space. I will now hand you over to Ms. Puran, who will be doing this section.
Good morning, everyone. All right, so first we're doing the introduction of planes in 3D. So in order for us to know what it is, I have a definition here. A plane in three-dimensional space is a flat, two-dimensional surface that extends infinitely in all directions, and it's uniquely determined by either three non-collinear points or a point together with two non-parallel direction vectors. So if you look below here, we have how they go from lines to planes. So lines happen in 2D. So you have a line going in a single direction. Now planes, they extend or they expand into three-dimensional space. So they spread out in space. So if you look over here, we have what a plane needs locating it. So the first thing what we need is a point. Then it could spread infinitely in all directions. So the next slide will simplify what that means. What defines a plane? A plane is a point plus two directions. A plane can be defined using the following. So we have the two different methods that we could use to define a plane. So we have the first one is the direction vector. So we have where there is a fixed point A, then you see it spreads along the three different sides. So the blue vectors B and C define the directions along the plane, where the point A defines the location. So it's color coded for you to see what I'm talking about. So point A anchors the location to both cases. Now, if you look over here to the normal vector method, we have the red vector N defines the direction away from the plane, and point A defines the location. So point A anchors the location in both cases. When we move forward, you would understand more what we're talking about. All right, so vector representation of a plane. So the vector representation of a plane, we have the formula R is equal to A plus SB plus TC, where we have R is the position vector of any point on the plane. A is the position vector of a known point on the plane. B and C are direction vectors, and S and T are scalar parameters. So this shows the plane is formed by moving in two directions. So if you look over here to the diagram, we have the fixed point A, which is 1, 2, and 3. Well, it's just an example. So it's color coded for you to look at it and try to understand where all the different things are pointing to. So the orange part we have here is the fixed point, which is A. The two directions are in blue. So the B and C are in blue. And the green points are any points where the position vector is. So we could clearly see it here. So any point here is X, Y, and Z on the plane. So an example of this vector form of a plane. So we have an example, we were giving a plane passes through the point A, 1, 2, and 3, and has direction vectors of B is equal to 2, -1, and 1. And C is equal to 1, 1, and 0. So the first step, we use the vector form of a plane, so which is the formula. Again, where A is the position of the vector of point A, B and C are direction vectors in the plane, S and T are real numbers. So step 2, we would substitute the given value from our problem. So A is equal to 1, 2, and 3. B is equal to 2, -1, and 1. C is equal to 1, 1, 0. So when we substitute that into the formula, we have R is equal to 1, 2, 3 in brackets, plus S is equal to, S open bracket 2, -1, 1, plus T open bracket 1, 1, 0. So the next step, we write in component of the rectangular form. So to make it easier, we just write it in this form and then we bring it down here. So 1 is equal to, the first one, which is A, is equal to 1 plus 2S plus T. Then we have S is equal to 2, which becomes 2, -S, and +1. And we plus T is equal to 1, which gives us 3 plus S. So any point on X, Y, Z on the plane is X1 plus 2S plus T. Y is equal to 2 minus S plus T, and Z is equal to 3 plus S. So if you look over here, we have a diagram representing the question. So it's all color coded again for us to understand better. So the point here, A is 1, 2, and 3, and we could see where B is and we could see where C is. So C here is in blue and B is in green. So any point on the plane, P is equal to X, Y, Z. So by moving any distance S along B and any distance T along C from A, we can reach any point on P on the plane. So the final answer now is the one that we just substituted here, and we just have it in this form according to the equation. So a point to remember, the plane is made up of all possible points obtained by varying S and T. So you heard me speaking about vectors and planes. So this is the relationship between vectors and planes. So direction vectors lie inside the plane. Cross product of two direction vectors gives the normal vector. The normal vector is perpendicular to the plane. The dot product helps form the plane equation. Now, Ms. Jaya is going to take you into the cross product and dot product so you will better understand what we're talking about.
Good morning, everyone. The cross product and dot product of planes in 3D. So here, here we have a diagram to show the vectors. We could use our finger, and our index finger here is on the x-axis, which represent vector A. The middle finger here, B, is on the y-axis, which represent vector B. And our thumb up, that's our perpendicular vector, represent A times B. And here is our angle. Okay. The cross product used to find a vector that is perpendicular, normal to a plane. So we are using the cross product to find the perpendicular vector or the normal vector to the plane. The dot product is used to write the equation of the plane using the perpendicular or the normal vector that we found from the cross product. The person who is sliding in, you do it one, please. Good. So here's an example. Suppose the two vectors in a plane are A, which is 1, 2, and 3, and B, 4, 5, and 6. So to find the cross product, good. So A times B. So we write that in terms of a matrix. So here is the matrix, IJK, and here is A, vector A, and here is vector B. To find the vector, we cover the column. So here we see we cover the I column, and we remain with a 2 by 2 vector, that is I. The second one, we cover the J column, and the 2 by 2 matrix remain, that is vector J. And we cover the column K, and we left with the 2 by 2 matrix for K. We use these vectors here now, I, J, and K. We find the determinant of each. So the determinant is AD minus BC. So for vector I, our determinant is -3. For J, our determinant is -6. And for K, the determinant is -3. So here we have point A, which is vector A, vector B, and the new vector that we find using the cross product, which is -3, -6, -3. That is the perpendicular vector or the normal vector. So we see C equal to -3I, -6J, and 3K. So this here is our normal or perpendicular vector. If a plane passes through the point 2, 4, 5, determine the equation of the plane. So to find the equation of a plane, we will use the dot product. So we are finding the equation of the same plane in part 1. So the formula to find the dot product is A bracket x minus x1 plus B y minus y1 plus C z minus z1 equal to 0. So we use our normal or the perpendicular vector from previous, which is -3, -6, -3. We substitute into the formula, so our normal vector goes outside on the formula, and our x1 goes inside of the formula. We substitute, we expand, as you can see here, then we group like terms. The next step, we have the constant could be divided by -3 because we have -3, -6, -3 plus 45. So we divide throughout by -3. Hence, our equation of the plane be x plus 2y plus z equal to 15. So the cross product of two vectors, a times b equal to vector a times vector b sine theta n. Direction of a times b is perpendicular to the plane containing the original vector. Cross product is not commutative, meaning that a times b is not equal to b times a. The cross product of parallel vector is a zero vector. So the dot product, if a equal to a1, b1, a1, a2, and a3, and b equal to b1, b2, and b3, then the dot product is a dot b equal to a b plus a2 b2 plus a3 b3. If theta is the angle between vector A and vector B, then A dot B equal to vector A times vector B cos theta. And A dot B are orthogonal, meaning perpendicular, if and only if A dot B equal to 0. To calculate the magnitude of a vector. So we see that we use the cross product to find the normal vector or the perpendicular vector. We then use the dot product to find the equation of the vector. And here, using the same vector, we want to calculate the magnitude. So we calculate the magnitude using both the cross product and dot product. So here, I calculate the magnitude using the cross product first. So these are the vector A, B, and C. The magnitude of the cross product is A times B equal to, So the formula to calculate the cross product, the magnitude using the cross product is A times B equal to vector A times vector B sine theta. So the magnitude is A times B. We root the perpendicular or the normal vector, and that gives us root 54. Then we find the magnitude of vector A and vector B. The magnitude of vector A is root 14, and the magnitude of vector B is root 77. My bad. The magnitude of vector A is root 14, and the magnitude of vector B is root 77. So we solve for the angle where we sub into the equation A dot B equal to vector A times vector B sine theta. That gives us sine theta equal to root 54 divided by root 14, root 77. We leave theta over the equal sign. We make theta the subject of the formula. We take sine over, it becomes sine inverse. And using a calculator, that gives us theta equal to 13 degrees. So over here, we use the dot product to find the same magnitude. But using the dot product, if you notice, instead of sine theta, we use cos theta. So A times B, it's supposed to be A dot B. My bad. A dot B equal to vector A times vector B cos theta. So here we have vector A and vector B. We times the values of x in vector A and the value of x in vector B. So we do that for B, and for the second part, we use the two values of vector. We use the two values. Oh, we use the two values of x for the first one. We use the two values for x for y for the second one, and we use the two values for z for the third one. So that gives us 4 plus 10 plus 18 gives us 32. So 32 equal to, so we know that the magnitude of vector A from over here is root 14. And we know that the magnitude of vector B is root 77. So I didn't go ahead and do that a second time. So we just put it into the formula cos theta. So here we make theta the subject of the formula, and that gives us theta equal to 13 degrees. So here we see that using the cross product or the dot product, we could still find the magnitude of a vector. So here is the diagram. The magnitude, the 13 degrees is here, that angle there. So in a nutshell, we use the dot product. We use the cross product to find the perpendicular or the normal vector. We use the dot product to find the equation of a vector. We could use the cross product to find the magnitude of a vector. Also, we could use the dot product to find the magnitude of a vector as well, using the formula A times B, vector A, vector B, sine theta, or A times B, vector A, vector B, cos theta. And that's it for the dot product and cross product. I will now hand you over to my next colleague.
All right, so looking at the normal vector, which is perpendicular to the plane. So first, the normal vector is a vector that is perpendicular at 90 degrees to a plane. It is usually written as n is equal to ABC. The normal vector tells you the orientation or the tilt and direction of the plane. Every plane has many parallel normal vectors, but they all point in the same direction. The normal vector is used to form the Cartesian equation of a plane, ax plus by plus cz equal t, which we will be looking at in the next few slides. Now, if you change the normal vector, the plane changes. The plane changes direction, sorry. So over here, we see the normal vector here, which is perpendicular to the plane, and the fixed point A is in orange. So you see all the different points pointing in the same direction. All right, so looking at the equation here, the standard Cartesian equation, so we have to use this to find the normal vector. So looking at the diagram, again, we have n is equal to vector A, B, C. It's a fixed plane. You have your red line here, which is perpendicular to the plane. It's an infinite plane. Now we have an example here. So it says, state a normal vector to the plane 3x minus 5y plus 12z minus 7, 0. So step one, you have to write the equation. So we write the equation, then we identify A, B, and C. So step two, after identifying A, B, and C coefficients, we write it in the state of a normal vector. So n is equal to vector 3 minus 5, 12. So this is very simple. So you could see here again where the point would lie. So the Cartesian equation of the plane is the standard algebraic way of describing a plane in 3D using x, y, and z. So ax plus by plus cz equal d, where a, b, and c are normal vectors that are perpendicular to the plane. And x, y, and z are any points on the plane, and d is the constant. So looking over here, you can see where X, Y, and Z is pointing. So the next slide will have how we derive the Cartesian equation of a plane. So the Cartesian equation of a plane in 3D again is AX plus BY plus CZ equal D. So the first thing you do is you start with a point on a normal vector. So the point here is a point on the normal vector. So let the plane pass through the point X, Y, and Z. And you have a normal vector, which is N, it's vector A, B, and C. So the normal vector is perpendicular at 90 degrees to the plane. So that is this red line here. Number two, consider any point on the plane. So let P, X, Y, and Z be any point on the plane. The vector from PO to P is this. So this here again is our normal vector, and this here is point P, which is X, Y, and Z. Step 3, you use the dot product. Since N is perpendicular to the plane, it is perpendicular to every vector in the plane. Therefore, N dot PO, P is equal to 0. So we substitute A, B, and C dot X minus X0 plus Y minus Y0 plus, am I saying that correct? Y or YO. Z minus Z0 is equal to 0. Step 4, expand the dot product. We expand the dot product here, and then we have A is equal to X minus X0 plus B, Y minus Y0 plus C, Z minus Z0 or point Z. So it's equal to 0. And we do the same thing for the others. And we have let D is equal to AX0 plus BY0 plus CZ0. So the key idea here is that a plane is completely determined by the point on the plane and a normal vector. So all points x, y, and z that satisfies ax plus by plus cz equal d lie on the same plane. So the final result here is the Cartesian equation of a plane is ax plus by plus cz equal d, where a, b, and c is the normal vector perpendicular to the plane. And again, x, y, and z is any point on the plane, and d is your constant. So an example of the Cartesian equation. So we find the Cartesian equation of a plane that passes through the points A, 1, 2, and 3, B, 2, 0, and 1, and C, 0, 1, and 4. So step 1, using the general Cartesian equation, we will find the constants A, B, C, and D using the 3 points. So we substitute the points AX plus BY plus CZ equal D. So for A, 1, 2, and 3, we substitute those into A1, B2, C3 equal D. Then we would have this as equation 1. So for B, we substitute again, and C we substitute again. So the first equation we have is A plus 2B plus 3C equal D, which we make equation 1. Then we have 2A plus C equal D, which is equation 2. And B plus 4C equal D is equal to equation 3. So step 3, you eliminate D by equating. So 1 is equal, equation 1, we have A plus 2B plus 3C is equal to 2A plus C. So when we solve for that, we have 4 in the end, which A is equal to, this here is equation 4. What am I saying? This is equation 4. So 2, we equate equation 2 to 3, and then we have equation 5. So step 4, we solve the simultaneous equation by substituting 4 into 5, equation 4 into equation 5. So when we substitute that, we solve for C, which is C is equal to minus 3B. Then we substitute it into equation 4. So when we find that, we have A is equal to minus 4B. So the next step we have is we choose a value. We let B equal 1, then A is equal to minus 4, B is equal to 1, and C is equal to minus 3. Step 6 now, we find D. So use any point. Example A, in equation A, we have 1, 2, and 3. So we use any point and we solve. So we have D is equal to 11, which is our constant. So the final equation of a plane we have here, we substitute all the values into the formula. So we have minus 4x plus y minus 3z equal negative 11. Or in standard form, minus 4x plus y minus 3z plus 11 equals 0. So some key points to remember, we only use the Cartesian equation. We substitute the 3 given points to get the 3 equation. We solve for A, B, C, and D, and the equation represents the plane through A, B, and C. So we have a diagram here that shows you the different points on the plane. All right, so I'm going to hand you over to Abigail.
Okay, so I will be taking us through what happens when planes intersect. Please click next. Okay. So when planes are in a 3D space, they will eventually touch, but they don't just touch, they intersect. And when they intersect, they form a straight line. And this line is infinite, meaning it moves forever in both directions. And this line of intersection is perpendicular to the normal vector of both planes. And there's some images here. As you can see, there are two planes there in the top image, and they're intersecting, and it forms a straight line, the straight line being M. The only way they wouldn't intersect is if the planes are perfectly parallel, as you can see in the bottom diagram. They do not intersect because the planes P and Q are perfectly parallel. Okay, so how to find a line where planes intersect? So to find a line where planes intersect, we first need to find the direction of the line that is represented in this diagram here. And then you find a shared point that goes through these lines. As you can see there, the point is V, and it goes through the direction of lines. And then we write the parametric equation. I'll take us through an example to make it a bit easier to understand. Okay, so the question says, find the angle between the planes x plus y plus z minus 1 equals 0, and x minus 2y plus 3z minus 1 equals 0. We're asked to find their intersection. So the first thing we do is we find the angle. Now, we find the angle using this this formula here, cos inverse of n1 times n2 over the magnitude of n1 and n2. So to find the angle, we use the dot product on the top part, which is the n1 times n2. And then on the bottom, we find the magnitude. And then when you work that out, you'll get 72 degrees using this same formula here. So the angle between them is approximately 72 degrees. So now, to find the intersection, we use the cross product like Miss explained earlier. You set it down in this matrix format and you solve it. So when we solve it, we get 5, -2, and -3. So now this here gives us the direction. We still need the point, the anchor point, if you will. So to make math simpler, we just set z equal to 0 because the problem gives us 3 unknowns and we have 2 knowns. So we select a value for one of the variables. We put z equals 0 just to make calculation easier. So when z is equal to 0, that comes out of the equation because again, it's 0. So that leaves us with x plus y equals 1 and x minus 2y equals 1. That's what we get from the first, the question. So you solve for x and y by using the elimination method. And when you solve, x would be equal to 1 and y would be equal to 0. So then we write it in the form x, y, z. So it's 1 because x is 1 and the 2 zeros. Y is 0 and z is also 0. And then to find the equation, the parametric equation, you add the direction vector to the starting point. So x would be 1 plus 5t. Y would be just negative 2t alone because that's 0 there, and the same thing with z2. And that is how you find the parametric equation of where planes intersect. So applications can be used in engineering design, architecture and construction, computer graphics and animation, aviation and navigation, robotics, and physics simulations. So it's quite important. So these are some important formulas to note. Feel free to take notes of the formulas. And just to conclude the presentation, a plane is a flat surface extending infinitely in 3D spaces. Planes can be represented using vectors and equations like we explained earlier. The cross product helps determine perpendicular vectors. The dot products assist in forming plane equations. Plane intersections form lines in space, like the diagram showed earlier. And understanding planes is very important in geometry, engineering, and computer graphics. And this brings us to the end of our presentation. If you have any questions or comments, feel free to say.
Oh, it's